Okay, the next is conditional So we talked about the conditional distribution. Now how do we calculate the conditional expected value? So PMF f y given x is the conditional distribution of y given x, which is sum of all the values of y f y given x should be 1 for for this conditional distribution. Now it is called as a conditional PMF, but it is just a PMF really. So probability of y's for all values of x have to be, or so sum of probabilities of y for all values of x should be 1. So expected value of y given x is equal to x is equal to sum of y and f y given x. So expected value of y given y is equal to x is going to be sum of all the values of y times y given x. And why is that? Because expected value for a random variable is always going to be the say expected value for random variable x is when x can take values x1 x2 x3 is going to be the x1 times probability of x1 x2 plus x2 times probability of x2, and this is exactly what we are doing here for all values of y, and f y is equal to x is just the probability of given by f y is equal to x. So that is why the expected value of y given x is all values of y given fx, and this is called the conditional expected value. So it has a very interesting feature that it depends on the value of x. So it is a function of x, and it is also, so we can also write the expected value of y given x is equal to x, because the probability of y given x is going to change, so it is dependent on the values of x. So you can also write it as expected value of y is x. It is a function, this whole expected value is a function of x. The expected value itself is a function of x. So it itself is a random variable, and we can call it as e of x. Basically it's an f of x, but because f we have already talked about, so we call it an e of x. So expected value of x, expected value of y is equal to the expected value of e of x that is expected value of y given x. E of y is equal to, now this is a very critical formula which is used quite often, is expected value, and this is actually expected value of y is expected value of e x, that is expected value of e y given x, which is nothing but this. So there is expected value, and then there is an expected value, and that is the expected value of y. And this is a formula, and this can be proven mathematically also. Which this is nothing but mean of the mean value of y given x. Now we would know that expected value of y given x is going to be xp. Instead of n, we are using the x here, because we know that for binomial distribution the expected value is n times p. So expected value of y would be expected value of xp, and since p is the constant, it will come out. So p expected value of x. Okay, now the other thing, question that we will explore is, suppose x and y are independent random variables with the PMF of f1x and f2y, and let z be another random variable which is x plus y. And if we consider a statement that conditional PMF of z given x is equal to x is f2 z minus x. So this is a very complex little statement. How do I prove this statement? So let's consider x for a second. X, number of heads in 5 tosses of a coin, and consider y as number of heads in next 7 tosses of a coin. So there are two separate random variables, and z then will become x plus y, which is just going to be number of heads in 12 tosses of a coin. Now probability of z given x is equal to x, for example, say x is 1, then if z is equal to little z is equal to 4, then x is equal to x is 1, then y is equal to little y has to be 4 minus 1 is equal to 3. Right. So how's that? Because z is equal to x plus 1, right? So if we think that x is 1, then z, for z to be 4 and x is 1, y is equal to little y, because z is x plus y. For z to be 4, y has to be 4 minus 1 is equal to 3, which is conditional PMF of z given x is equal to x becomes f2 z minus x. So probability of y, that is f2, is z minus x. But y is independence implied here. Probability of z given x is equal to x is the same as probability of y is equal to little y, x is equal to little x when y is say 3 and x is say 1, because z is equal to x plus y. Z is 4 and x is 1 and y is 3. So probability of z is equal to 4 given x is equal to 1 is the same as probability of y is equal to 3 given x is equal to 1. Now probability of y is equal to y given x is equal to x is equal to probability of y is equal to little y and x is equal to little x divided by probability of x is equal to little x, if x and y are independent events. Thus, if x and y are independent events, then this actually becomes probability of y is equal to y multiplied by probability of x is equal to x. So probability of y is equal to y given x is equal to little x becomes probability of y is equal to y times probability of x is equal to little x divided by probability of x is equal to little x. This gets cancelled. So probability of y is equal to y given x is equal to x becomes probability of y is equal to y, but y is equal to z minus x because z is equal to x plus y. Thus probability of z given x is equal to x will become probability of y is equal to y. Because we have already written this thing over here that probability of z is x actually the same as here, so that is why we get to this statement here. Probability of z x is equal to x is probability y is equal to little y, and probability of z x is equal to x becomes probability of y is equal to z minus x, because that is the f2, which is basically f2 is z minus x. So if we want to say then joint PMF of z and x will be f2 z minus x, which is just a PMF of probability y is equal to y and probability of x is equal to x, which we have seen earlier. Multiplied by f1 x, and the probability mass function of z will be sum of all values for all values of x, f2 z minus x times f1 x. The sum that provides the PMF of the sum of two independent random variables is called the convolution sum. The sum that provides PMF of the sum of two independent discrete random variables is called convolution sum.